Please welcome the stage, Jon Edwards! So we on? Great. Should we start with the song? No, that's at all.
It's only a cheap guitar, don't worry.
Right, shall we start with the song? No, I'm not going to sing actually. We'll just leave it there. I'm just tall enough to bang my head here. So, we might recognise that, anybody?
It was music.
It was music. It was Johnny Be Good, which was made famous in the 80s by this guy, Martin McFly, in the film Back to the Future, which has had a few calls tonight. But it was actually written a little bit earlier by a guy called Chuck Berry, who was a convicted armed robber and people smuggler, but he's probably better known for actually inventing rock and roll. And tonight I'm going to celebrate the life and work of a guy who led a musical revolution in an increasingly closed-minded establishment. And of course I'm talking about John Newlands, who was a Victorian chemist from Surrey. And 150 years ago, he went to the Chemical Society of London on Piccadilly, which is now the Royal Society of Chemistry, where I work. And he presented to them a crazy new idea, never been seen before. He'd ordered the chemical elements into a table, a periodic table. In 1864, this was the first one to be seen. And the learned gentlemen of the Chemical Society of London sat in their seats, listened to him speak, pissed themselves laughing and ejected him from the premises, because his table was not based on scientific theory at all. It was based on musical theory. Why did he do that at all? Let's have a quick look at his table. So what we've got here, based on his newly minted Law of Octaves, is John Newland's periodic table from 1864. And it's based on this Law of Octaves, which goes, if you order the chemical elements by their relative atomic weight and group them repeating every eighth element, just like octaves, then the elements on the same line will have similar properties. That's a very charitable explanation of that law. Let me correct it a bit. If you line up all the elements in order of their atomic weight and group them in eights and swap around chromium and titanium and cerium and zirconium and uranium and tin and just group a load of them for no apparent reason, then some of the elements on the same row have similar properties. What do you expect? It's musical theory, not science theory. Anyway, so this was his table based on his Law of Octaves. And what did that have to do with anything? Well, he was musically obsessed. He thought we could find the music in chemistry. So just quickly, for people who don't know what an octave is, here we have a diatonic scale, and I'm going to pretend it's A major. Musos in the room, forget that I left the keys to the guitar off, please. The octave is the interval between one musical pitch and another with half or double its frequency. And to demonstrate that, I can quickly show you the guitar. So there we've got an A and an A. Which, if I can use this at the same time, the top and the bottom of this scale are an octave apart. And if I play those two things together, if my guitar were in tune, you could hear that it resonates quite nicely. There's apparently some physics behind this. And so let me just take the A string here. If I play it open, then it's tied here and here, and it vibrates 110 times a second. Your ear hears that note. If I double the frequency by halving the wavelength, or going to the 12th fret, it's an octave higher. So you hear that. And that's enough physics, though, because this is my chemistry bit. Let's go back to the chemistry bit. So John Newland's table, he died in obscurity. Everyone thought he was ridiculous. But 150 years later, I have access to knowledge and tools that he didn't, that let me really discover what he was onto. He was definitely onto something. And I'm going to take his rules really, really literally and show you the connection he made. And I'm going to use the two things that he didn't have, organic chemistry and rock and roll music. So let's just take the first group here. He said that you repeat the groups of elements as you would in a musical scale. So I'm going to literally say hydrogen is A, in this case, or the first, the tonic in the scale, and then go up through these. I don't know why G is beryllium. They changed it for some reason. And then through carbon, nitrogen, oxygen, 5, 6, 7. So let's see if I can literally play some chemicals using John Newland's rules, what it sounds like. And let's start with the two most common elements in organic chemistry, hydrogen and carbon. And they are at the first and fifth positions of the scale. Let's take a really simple organic molecule, methane. So, just the most simple organic molecule just has carbon and hydrogen in it. We use Newland's nomenclature here, 1, 5, and 1. What happens if I play that? It's all right, not bad. That's an A5, or a power chord as it's known. 99% of rock music is made of that. It's kind of boring though. Who heard of a song with one chord in it? So let's make a few more additions and atoms in this thing. Let's extend this chain to ethane, which has 2 carbons in the chain. And if that, I play. Okay, somewhat better, but still a bit boring. How about butane? That's patio gas, basically. So, how does that sound? Not too bad. How about octane? 8. Still pretty good. What about this one? It's high octane. So that's hilarious, but I've really stopped at a very boring set of one chord. Let's introduce the third most common element in organic chemistry, which is oxygen. And I'm going to use a very simple organic chemical here. Methanol, do not drink. Very bad for you. So using John Newland's nomenclature, again, we've got the first, the fifth, and the seventh. Seventh is a very important note in music. Chords with the seventh in indicate that you're kind of going somewhere. Let me play you methanol just to demonstrate. Okay, so it's kind of mysterious. It's kind of going somewhere. Got that 7 in it. Off it goes there. So there's loads of that in jazz, loads of that in classical music. It doesn't sound particularly rock and roll. So let's introduce the fourth most common element in organic chemistry, which is nitrogen. And I've got a really simple, again, organic chemical here, methylamine. By the way, I'm not an organic chemist. I've made the names up. So, 1, 5, and 6. Now, 6 is a much less common interval used in chords. And let me just play you. That doesn't sound like anything. But it's used in jazz quite a lot. It's not so much used in classical music, but it's very much used in rock and roll. But it doesn't sound very rock and roll. The reason is I've taken it out of context. And what I'm going to do is start adding more stuff to the chain here to give it a bit more context. So let me ram on the ethane that I had before, 2 carbons, onto this, to make what I'm calling ethyl methylamine. Maybe true. What happens if I play this one? Hey, now we're getting somewhere. Doubters. So I've lost the oxygen though. Let's ram on some more stuff. What about that one? Now we're getting there. But if you've heard a status quo song, you know you never just hear one of those riffs. You hear infinity of those riffs. So when chemists want to use repeating units, they put brackets around it like this. And for those at the back who can't read, we have polyethyl methylamine, methyl methylamine, ethyl. Which, of course, finally found the rock and roll music in chemistry, I think, which is fantastic. So John Newland's vindicated. The music in chemistry, I think he was really on the right track. The one problem with this molecule is it almost certainly doesn't exist. And it would be really difficult to make. In fact, if you were able to make this, you'd be an award-winning materials scientist. And as I said, I work at the Royal Society of Chemistry. And we give awards for great chemistry. And if you were to get the award from the Royal Society of Chemistry for excellent materials science, I was really pleased to learn that the actual no-shitting name of the award is the John B. Goodenough Award. Which I think is very apt. Thank you very much.